Hello, welcome to section 2.2. Today we are going to be talking about introductions to polynomial functions, and most importantly, we are going to be discussing the end behavior of different types of polynomial functions. So let's start by analyzing polynomial functions with multiple terms. One important characteristic is the end behavior. So how does the polynomial behave at the endpoints? So usually when we have a graph of polynomial, it's either increasing or decreasing. Is it going to infinity or negative infinity? So we want to start by what's going on as x approaches infinity. So what happens to the function as x goes to infinity? X approaches infinity. That means that x becomes very, very large. As x goes to negative infinity, we have it's becoming a very, very small number, a very large number to the negative direction. Now, what does that behave when the function entirely or the y value, so this is the y value, goes to infinity and the y value goes to negative infinity? So we begin by discussing how does a polynomial look like. For a polynomial f of x, these a sub n's are your coefficients. Those are your coefficients of your leading term. So x of n, this n is your leading term. We can observe that it will have a general direction. And who will determine the orientation of the graph? It's that first term, a sub n, x to the n. Now we have to look at the power of the polynomial and what happens when the coefficient is either positive or negative. And that's when we discuss endpoints. So when we have the function a sub n, x to an even, so 2n, an even function, an even polynomial, what happens as x goes to negative infinity? So a sub n is positive, our coefficient is positive, but what happens as x approaches negative infinity? Well, we have a negative infinity to a positive power. That means that the endpoint will still be positive. Same thing here. So my endpoints of those particular values, what happens as it's approaching negative infinity, my endpoint, so see how my x is going to negative infinity, but the y value is still positive. Now what happens as x goes to positive infinity? I'm going this direction. So for example, as x goes to infinity, my y value will also go to infinity. So here I'm looking for an x squared, an x to the 6th, an x to the 8th, and my coefficient a sub n is positive. So a sub n being positive will always have f of x always going to positive infinity. Now we will have a different case if a sub n is negative. Now how will that change? Well, now if a sub n, the leading coefficient, now let's look at this leading coefficient, a sub n. What happens when a sub n is negative? If the coefficient is negative, what happens at x sub n goes to negative infinity? So we have a negative a sub n, x to the 2n, or n as n being an even number. Now we will have this behavior. As x goes to negative infinity, my y will also be negative. So now this is negative x squared, a negative x to the 4th, a negative x to the 6th, and so on. My power is even, but my leading coefficient is negative. So here I have to focus on, okay, what's my leading term? My leading term is negative, so my y value will be negative. If my a sub n is positive, then for an even polynomial, then my y value will be positive. Okay. Now those things change if my polynomial is an odd polynomial. If I have an odd polynomial, then a sub n is positive. Then I have a scenario like x to the third. What happens as x goes to negative infinity? Well, then y will go to infinity. So this term, even though a sub n is positive, but a polynomial is odd, then you will have this behavior. As x approaches negative infinity, y will be negative infinity. Now, as x approaches positive infinity, so as x approaches positive infinity, so going this way, as x approaches infinity, then y will also go to infinity. So then notice here that my graph, as x is going down, then y is going down. As x is going up, then y is also going up. Now that's when your a sub n is positive. But what happens if a sub n is negative? If I have negative x cubed, now what happens? Your orientation changes. So as x goes to positive infinity, your f of x will go to negative infinity, and I have this behavior. As x approaches positive infinity, my y will go down, so it's reversed. Now, as x is going to negative infinity, which is this direction, as x goes to negative direction, then y is going up. So as x goes to negative infinity, your f of x will go to positive infinity. And that is called the end behavior. That's a negative x cubed, a negative x to the fifth. It could be a negative 7 x to the seventh. My a sub n is negative, then I will have this behavior as x approaches negative infinity, as x approaches positive infinity. So using that information, we are going to go to the following examples. Alrighty, so now let's go over some examples on how to determine the end behavior of a graph. So the first thing you have to notice, step one, is what is the leading coefficient? What is the leading coefficient? In this case, the leading coefficient is who has the highest degree and the coefficient. So in this case, the coefficient a sub n, x to the n, x to the n is x to the fifth power, and a sub n is 1. So 1 is greater than 0, that means it's positive, and n is odd. So then we will have the end behavior if we look at our notes, and if we recall, if a sub n is positive and we have an odd value, then what happens as x approaches infinity? What will happen to our function? Well, then as x goes to positive infinity, my function f of x will also go to infinity. And how can we check that? Well, we can check by two ways. We can graph the polynomial, we can graph, or we can test the function. How will the function behave? Will it go to positive infinity or negative infinity? So notice how x to the fifth dominates. What happens as x becomes a large number? If I have a large number to the fifth power, it's going to be larger than the negative 5x cubed. So I know that when I test the function as x goes to infinity, the entire function will go to infinity. So let's go ahead and actually graph this polynomial. Let me use my Calculate 84. That way I can share my screen and you are able to see the graph of that function. So what I have y equals, I have x to the fifth power minus 5x cubed plus 4x. That's the function that I have, and then I'm going to select graph. Notice here that this is the function of that polynomial, the graph of that polynomial. What happens as x goes to that right side? Notice that the y will also go to that positive direction. So that proves exactly what I'm talking about. As x goes to infinity, then the entire function will go to infinity. And that's because we have an odd polynomial with an a sub n being positive. Now here, this one's different because you can't really distinguish what the degree is. I have a leading coefficient of a -2, and look at the degree. I have an x term, and then I have an x to the third. So technically, this is x cubed and then x to the first. So x times x cubed, it's an x to the fourth. So my leading term will be -2 x to the fourth. Now here, my a sub n is negative, but s of x of n is odd. Sorry, n is even because 4 is even. So we have an even polynomial, but my coefficient is negative. And I had to do a little bit of work because I have an x and an x to the third. So whenever you have a polynomial that's kind of divided, you have to pay attention to the degree of each of the divided terms. So I have an x and then an x to the third. So combined is an x to the fourth. And don't forget that there's a negative in the front. So it's a -2x to the fourth. That is the dominant term. That is the dominant term that I'm going to look at. So a sub n is negative and n is even. So what happens as x approaches infinity? And what happens as x goes to -infinity? So first, as x approaches infinity, what will happen? -2x to the infinity to the fourth power, but I have a negative in here. This is going to go to -infinity. So f of x, so this function, f of x, will go to -infinity. Here, -2 to -infinity to the fourth, -infinity to the fourth power, it's still positive because it's an even polynomial. So this is still a -infinity. So it doesn't matter the orientation here because I have an even polynomial, but my leading coefficient is negative. So then this will behave this way. So as x approaches -infinity, my y value will go to -infinity. As x approaches positive infinity, my y value will go to -infinity regardless. So we saw that both when x is positive infinity and when it's negative. Let's go back to the first one. So we saw what happens when x is positive infinity. What happens when x is negative infinity? Well, if we test the function, if we have a negative x value raised to the fifth power, my solution will still be negative. So f of x will go to -infinity. And that's because we have an odd polynomial. Same, we can also look at the graph and test the function. So remember, if we go back to our screen, what happens as x goes to -infinity? So you're going now this direction. My y is negative. So you can look at it based on a graph, substitution. And then if we remove this graph, and let's put in the new graph, and the new function is this -2 parentheses x minus 5 close parentheses, open parentheses, x plus 1 close parentheses to the third power. And then we're going to graph that. See how now, if I'm going to zoom out a little bit, see how my graph is going down? As x goes to -infinity, my y is still negative. As I go to the right direction, y is still negative. So see how they're both going pointing down? That's because my leading coefficient was negative. So having a negative leading coefficient matters when you have an even function. It matters when you have an odd function. Okay. So that is n behaviors. Now, determining the zeros of the functions defined for which f of x is equal to 0. When I'm looking at zeros, that means I'm looking for x-intercepts, how many times it crosses the x-axis. So determining the zeros of the functions defined by this third degree polynomial. So one way to find zeros is letting f of x equal 0 and finding x. So it's like you are finding your x-axis, your x-intercept. So 0 is equal to x cubed minus 5x squared minus 16x plus 80. Now, once we have this, we have one term, two terms, three terms, four terms. we can factor by grouping. So we use the grouping method to factor and factor. So what can we factor from the first term? We have an x squared to factor. That leaves us with an x minus 5. The second term has a negative 16 because 16 and 80 have 16 in common. And that gives you x minus 5. Now this is set equal to 0. Because I have these terms to be the same, I can pull it out as one factor to be x minus 5. The other factor is x squared minus 16. They're both equal to 0. Now I can split using the zero product property, ZPP, the zero product property. The ZPP is the zero product property. And what does that mean? That zero product property means if this product and this product equals 0, each individual product is set equal to 0 automatically. So x minus 5, set that equal to 0. X squared minus 16 is equal to 0. Now here, this is easy to solve because that gives me x equal 5, moving the 5 over both directions. Now here, this you can use the square root property, move the 16 and take the square root of both sides, or you can factor difference of squares, x minus 4, x plus 4. So this is difference of squares, difference of squares. You set each individual again. X minus 4 is equal to 0, x plus 4 is equal to 0. And you solve simultaneously. X will give me 4 in this area, and then I will have an x equal negative 4. And I find exactly all of my 3 zeros. So one of the zeros will be 4 comma 0, negative comma 0, 4, negative 4 comma 0, and 5 comma 0. So these are my 3. That is 3 solutions, 3 zeros from this cubic function. Okay. So you have to factor, you have to set it equal to 0. Now, number 4, what happens once you factor? We have to look at the multiplicities. And what does that mean? That means how many potential zeros we can have, the multiplicity k. So we always have to have in this factored form x minus c, where c can be any value, even 0. So we want to first determine the zeros. So that means we're going to set f of x equal to 0. And then we are going to look at each individual multiplicity. So I'm going to pause the recording here to start this problem.